Good evening, everyone. The webinar will be starting shortly when everybody joins. Welcome to tonight's session. Good evening, everyone. Thank you for joining tonight's session. We will be starting shortly whilst more people are joining the session. Good evening, everyone. Thank you for joining tonight's session. We will be starting shortly. Good evening, everybody. I'm Alison Griffiths and welcome to tonight's session, the IET Northwest Midlands talk. Welcome to the session and thank you for joining this evening. This is your professional home for life. Some of you may have already been to lectures previously and others may be your first visit. If you're a member of the IET, you can download a CPD certificate for joining this session, which shows your continuing professional development. We have links on Facebook, YouTube, where you can view this lecture in the future and past lectures. And you can have a look at what the next events are coming up. The next event is on climate change, and we haven't decided the date yet. So keep checking the local area network web link. The links will be posted in the chat and they're also on these slides. So we provide career management courses and training, mentoring towards your professional registration. You have journals and books, IET TV, where you can view lots and lots of videos of other talks. You can get involved in outreach work, encouraging young people to join the engineering profession. So without further ado, I would like to introduce the host for the evening, Amelia.
Thank you, Alison. Welcome, everyone, and thank you for joining us tonight. The topic for tonight is AC and DC protection for the UK power system. We have joining us today, Brian. Brian has worked in the industry for 25 years, and I've had the pleasure of knowing him and working with him for almost 10 years of those 25 years. Brian owns his own company, and he'll talk more about that during his introduction. He's also a fellow of the IET. So we are happy to have him come back and deliver a talk for us as a member of the IET. He also lectures on this topic, AC and DC protection. So I'll take this opportunity to introduce to you Brian Kirby.
Hello. Okay. Are we ready?
Yes, we can hear you, Brian, and we can see you too.
Good. And I shall share my screen and we can begin. Okay. So, hello everyone, and welcome to my presentation this evening on AC and DC protection for the UK power system. As Amelia has introduced me already, I'm Brian Kirby. I've got 25 years experience of working in this industry, and I have got lots of useful knowledge that I'm hoping to share an overview of with you, because we need to bring more people into this power systems protection field. Well, engineering as a whole needs people. So what I'm going to talk about today, I'm going to do a quick overview of myself, where I come from, my career and technical associations that I have. I will then introduce you to the UK power system, how it's structured and key components within it that are of interest when you're looking at protection. I will then quickly do a comparison of AC and DC protection requirements and how they are similar yet have significant differences at the same time. I will spend a bit of time looking at the key protection principles for AC power system networks. And then similarly, I will look at the key protection for DC networks. Well, DC protection as applied on high voltage distribution, on high voltage transmission systems today, and potentially distribution in the future. I will then look at what are the active developments in the world of protection today. And then finally, I will look at the future challenges for the UK, what challenges the UK is actually also a global challenge, and draw some conclusions from all of that. So I have a career, as Amelia said, I've been working in power system protection for 25 years, but I have an earlier career preceding that, working in the Ministry of Defence and academia with the University of Birmingham, working on radiation dosimetry and marine navigation systems. But then in '97, I moved to the Protection and Control department in Stafford, and I've been in that industry ever since, through all the iterations of companies, until in 2014, I decided to set out on my own and form a consultancy, Kirby Automation Limited. In the last 6 or 7 years, I've also done lecturing on power system protection, both with Staffordshire University and currently with Brunel University. I've been a member of the IET, as it is now, was the Institute of Electrical Engineers back in the 90s when I joined it. So I've gone through the whole suite of membership levels, from student member to associate member and chartered engineer, and then today fellow. IEEE, I didn't join until well into my career, straight in as member, senior member, and I've grayed out fellow because that's my goal, but I haven't actually got to that point yet. I'm also a member of CGRAE and actively take part in some working groups that are going on. I've got membership of the Association of Project Managers, having achieved their certificate level. My degree was from the University of Sunderland, which some of you may recognise my accent is from the northeast of England. So that was my local university. That's obviously in the days before I became involved with power system protection. And then Staffordshire University, I've done a master's degree and a degree in management and leadership, a diploma rather. And Brunel University, I've become a member of their Institute of Power Systems. So let's look at the UK transmission system. So today, the UK is divided into 4 regions from a transmissions perspective. Northern Ireland has its own electricity network. Scotland is divided into 2 parts. Scottish and Southern does the northern part, the Highlands effectively, and SP Energy Networks does the lowland, which is the main population centre where Glasgow, Edinburgh, places like that are. And then England and Wales are all part of National Grid, but collectively they are responsible for the transmission of power at 132 kV and above in the UK. These are state appointed bodies. So since 1990, these have been privatized. So they're funded through your energy pills, which go in through the regional distribution companies. As you can see, if you look here as the border between England and Scotland, in England, predominantly the transmission system is at 400 kV. And then in the large urban areas, you also have a 275 kV network. But you don't really see a lot of 132 kV in the transmission system in England. However, in Scotland, you actually see quite a lot of 132 kV transmission as well, particularly in the Highland areas, because generally, apart from, say, Aberdeen, Inverness, the population density isn't that high. As well as having all of that AC high voltage running around the UK, we also have quite a few high voltage DC links with mainland Europe, either in service, in commissioning, or in planning. So if you look here, IFA, England, France, that's been running a very long time, but it's just recently been upgraded. IFA 2, I think, is imminent. Similarly with Electlink. Electlink is an interesting one. They've actually put cables through the Channel Tunnel in order to achieve that, through one of the service tunnels. And then there are links to Denmark, Norway, all over Europe. And of course, then there are a couple of established links between mainland UK and Ireland, which supply energy usually from the UK to Ireland. So if we now look at distribution networks, there are 10 distribution networks in the UK and Ireland, because even though Ireland isn't part of the UK, it is electrically connected to Northern Ireland, which is part of the UK. So there has to be some collaboration between those 2 parts. As far as I'm concerned, and any people in sort of the region where I am, I'm part of number 7, which is Western Power Distribution, and they cover from down in Cornwall all the way up through Wales, the Midlands, across into East Anglia. Lincolnshire, not East Anglia. And these distribution network operators are responsible for taking the voltage levels. Oops, sorry, let's go back. Taking it from 132 kV down to the 415 volt ultimate supply that is fed to your homes and businesses. Okay, so in a conventional power system, we have a number of components that are there in order to achieve what we want, which is to get the power from where it's generated to where you want to consume it safely. We have generators themselves, which convert some form of energy into electrical energy. It could be thermal, it could be solar, there's lots of different sources. We then have power transformers, which are used to step voltage levels up and down, primarily because you can get more efficient transmission of power at higher voltages. Then we have switchgear, which can turn lines on and off, turn equipment on and off, and reroute the way the power flows around your networks. We have the actual lines themselves, which carry these currents and voltages around the network. Then we have measurement transformers, which let us see what's going on, so we can have some understanding of power flows and perform some sort of control. So if we look at generation, traditionally thermal generation was done by coal power stations and a few nuclear stations, and these would burn their fuel, heat water to run a steam turbine, which would then be driving a electrical generator. Coal stations are now becoming obsolete because of the carbon requirements. There's a lot of the CCGT, combined cycle gas turbine generators out there. Their big advantage is that they can be turned on and off very quickly, so they're good for a sort of meeting peak demand. But they all work in the same principle. They generate steam, and that can then turn the turbine, which can generate electricity. More and more today, we're seeing renewable energy being a large, if not total, part of our energy mix. Hydro generation has been around for many, many years, but it has the ideal profile for peak response, but you couldn't run the system full time on it because you continually have to replenish the stock of water required for these generation sites. What is becoming more and more common are the next two, solar power and wind power. Obviously solar power, you require sunshine, so it is limited to daylight hours. So in a climate like the UK, in the summer months, you can have long sunny days and get lots of solar energy. But then in the winter with short days, you're limited on the amount you can generate. Wind power, again, it's variable, but the reliability of your wind is greater at sea, which is why we're seeing lots of offshore developments. And particularly Scotland around the north coast has a very good stable wind flow. So Scotland is becoming quite a significant exporter of electricity from wind power. Geothermal and biomass are other smaller parts of the generation market, but they're still relatively small scale. So I won't worry too much about those these days. So here's a map from a few years ago showing offshore wind farms spread all around the UK. And there's a list. The key thing to take from this is that in 2020, there were 8 gigawatts of UK wind farm capacity, but capacity doesn't always generate to actual generated supply. So you always need some sort of reserve to be able to step in for when the wind isn't blowing. Power transformers are the links between the different sections of your network. They provide step up, step down and voltage levels for both transmission and distribution, and they can also perform some isolation of your network as well. And the typical levels in the UK, as I've mentioned, the transmission level 400, 275 and 132 kV, and then the distribution levels 132 kV, and then you'll see these are all multiples or integer dividers of 132 that will all go into there, so you can get an integer turns ratio for your transformer. Another important part of the network is your switchgear. So you need to know what your circuit breakers are rated for, so that you know what faults you're able to tolerate on the network, or you're able to clear on the network. Circuit breaker, as its name suggests, is simply there to open if you detect a fault and extinguish any arcs, and hence isolate that part of the network. Once isolated, you'll then usually open some sort of disconnector arrangement to permanently disconnect it until you've discovered what the source of the fault was. Or if you've got auto recloser, you might keep that closed and reclose the breaker, and then after so many shots, then you would open the disconnector and isolate the network. You also have earth switches, which are there to prevent any stray pickup of voltages once you've isolated the network parts. So overhead lines and cables are carried on pylons and poles. So here's a picture of all the different type of things you're likely to see across the network, from high voltage down to low voltage. Primarily, the UK uses overhead lines, and that's because the cost relatively is low, but that does mean they're exposed to any environmental factors, wind and rain, snow, etc. And also, sometimes if you have damaged conductors, you may have risks to members of the public as well. So in urban areas where you don't have the capability of running overhead lines through towns and cities, cables are more common. There's more planning requirements for cables, and the cost of installation is higher, but the advantage is you're not usually exposed to the public. But you do have the risk that any groundworks going on, someone digging up the road to replace pipes or put in foundations for a new building, may accidentally damage them. Offshore, cables are almost exclusively used because it's just not practical to try and run overhead lines over the sea. Finally, you need to be able to measure what's going on in order to have any idea of what actions are needed. So voltage transformers, the most common arrangement is the 3-phase to neutral voltage arrangement, as shown here. But sometimes if you have, say, a delta transformer, you may want what's called a broken delta VT, which will then give you a neutral displacement measurement as well as the 3-phase voltages. Current transformers will be 1 per phase, and you will be monitoring the current flowing in each line. Okay, so those are the components that we use in order to build our power system, as far as we're interested from a power system protection. And obviously there are things connected to the network like motors and other equipment that have special protection requirements, but we're not looking at those in this lecture. We're looking purely at the power system itself. So if we look at AC and DC power systems, if we compare the characteristics of the two, on an AC system, we have a sine wave. So we have a change of polarity twice per power cycle. That's at 50 or 60 hertz typically. However, on a DC system, you're supplying a constant, a nominally constant polarity. That means on the AC system, your inductance will cause a lag to the voltage with your current, whereas a capacitance will effectively cause the current to appear to lead the voltage. However, on DC systems, because you're not having this change in polarity, once your line's energized and charged, it has no direct impact. On an AC system, you typically, in the UK, see an angle of about 70 degrees lag. And there's also a bit of inertia in the system due to the rotating machines that are driving the generators. On DC systems, it's all power electronics, and there's no inertia as a result. It's all pure active power. Oh, sorry. Trip decisions on AC systems will be validated, because what you don't want is a false operation to disconnect your customers if you can avoid it, because there are strict penalties associated with that. So therefore, you can delay your trip decision and validate your choice before you turn the energy off. However, on a DC system, you don't have that luxury, because of the way faults propagate, you need to instantly make a decision. AC networks, 10 to 100 milliseconds or even longer, maybe at sort of low voltage distribution, you may have several hundred milliseconds to act before any serious damage is done to your network. DC protection, typically you have single figure milliseconds in order to operate. As a result, DC protection tends to be, fire first, ask questions later approach. AC protection generally is done by a dedicated device that sits on the network and then interfaces with your switchgear and any other control systems. Your DC protection generally is integrated into the converter technology that is driving your power electronics. Okay. So let's go and look at some AC protection principles. For those who are, those who are interested, that power station there is just off the A38 where it's junction with the A50, but I believe the cooling towers have now been demolished. So power system protection, why do we need it? And what do we need to consider when we're applying it? What type of fault are we going to see? And what classifications of protection are we considering? So why do we need protection? Well, protection is effectively a insurance policy. Any system, no matter how well designed, may have a fault occur. And if you want to protect it, you need to detect that fault and isolate it to limit the fault and to limit any disruption to any adjacent equipment. So here, our meter's monitoring away and it's in the green. It says, oh yeah, everything's fine. And then a fault occurs and our measurements go into the danger zone. So what we want to do is we want to isolate the fault, which means we disconnect the energy from that part of the network. So if you have a fault, it can lead to quite severe consequences if your protection either does not operate or is not properly configured. You can see here on the left a transformer fire, where if you allow the transformer to overheat, it can, particularly oil-filled transformers, they can cause explosions and various other incidents. Excessive currents may also cause conductors to burn or anything attached to it. You may get arcing, which will dissipate energy into adjacent equipment and also may interfere electromagnetically with other equipment. And you can also, if you've got other hazardous or explosive materials nearby, you can cause explosions with them as well. Secondly, any staff or public in the vicinity are in danger of electrical shock, either directly by contact with the equipment or even indirectly because you could actually induce a voltage in exposed metalwork nearby. They also, as you can see here from an oil fire, you can produce fumes either from the oil or from insulators, and these can be toxic as well. So you may need to clear areas when this happens. And UV arc flashing can happen, and this can actually cause blindness if observed directly. And then if nothing is done to clear the fault, it may evolve, and that means it actually will spread across your system, damaging and affecting other parts of the network. Voltage depressions and loss of supply can happen. You can have motor stalling. Voltage depressions will cause things like wind farms to go offline. So you actually lose part of the generation at that point. And if you lose synchronism, you may actually find that part of your networks isolate and become islands. And then you have to start doing shutdowns. And the biggest risk is ultimately you go to a full blackout and you have to do a black start again. However, as we know, insurance is a financial balance. You've got to look at the cost of protection against the cost of the loss of supply and the damage to equipment. So if you have a small transformer that's going to cost you £20,000 to replace, you're not going to spend £40,000 on protection for that. But if you have a high voltage transmission transformer costing hundreds of thousands of pounds, then £25,000, £30,000 on protection schemes is a good investment at that point. So it's always a cost balance. So the minimum cost has to be calculated to ensure that all faulted equipment is isolated. So you would look at what is the minimum we have to do to make sure we provide adequate protection. But then when you look at your total cost, there are a whole host of other things you need to consider. You will have relays, schemes, panels need to be wired and panel drawings done. You'll need to have studies to work out settings for your scheme. It will need to be commissioned. You may have to install new transformers to do current and voltage measurements. These systems are generally installed to operate for several decades, so you'll need to look at a maintenance repair plans. What do you do if the protection fails? Are you liable for repair to equipment as a supplier? Do you need to take out insurance policies of your own? And what is the lost revenue if the protection does operate when it shouldn't? All of these considerations need to be built into your costing. So here's a list of important considerations. And I've selected a few in bold, which are things that you have more control over as a protection engineer. Types of fault. Typically, the type of fault is dependent on the system that you're protecting, so you can't really control that. Similarly, types of protection available. Today, there are lots of different protection schemes available, and typically they're all available in a common form factor. A single device normally will do most of your protection functions. Speed of response is something you will be able to influence. This is important if you've got sequential protection schemes. The available measurements and CT and VT ratings may be under your control, but typically they're not. Typically they're set by the either the distribution company or the transmission company, who will have their standard availability for those things. The next two are the key things you need to look at from in terms of long-term operating. You need to be dependable but reliable. I will go into more detail on what those are in a later slide. Similarly with security and stability, I will address a bit more about those later on. Auxiliary supplies, again, most substations now will have some sort of battery backup system to run your secondary equipment, but usually that's something that the customer specifies. We need to be able to do discrimination of your phase. So if you have a single phase fault, you need to be able to identify that and select that phase for individual operations if that's what the customer wants. You also need to be able to work out where the fault is, particularly on long overhead lines, because you may need to send someone out to investigate what's going on. If you've got multiple zones of protection, you want to make sure they overlap so that there are no blind spots. In the UK, all protection run with backup and duplication schemes, so that your backup will be another form of protection to your primary form, and your duplication will be the same form of protection, but usually by another vendor to give you that common failure mode protection. And then cost, obviously, as we've mentioned. So if we come to look at the application of protection, speed is a key factor in our network. And the higher the voltage, generally, the faster you want to be able to clear your fault, because the more energy that is likely to be flowing through your system at that point. So fast operation will minimize danger and damage to the system. Very fast operation, and by that we're talking sub-cycle, so less than 1 power system cycle, which is 20 milliseconds in the UK. That is for usually for transmission systems, and it's to maintain stability. What you want to do is you want to clear the fault. If it's a transient fault, you may want to clear the fault and then reclose to see if the fault is cleared. And on transmission systems, that is quite often how they operate in the UK. You also want to discriminate where the fault has happened. As you can see on the right here, we've got various zones of protection. We have a protection zone around the generation, then around the bus bar, feeder, etc. all the way across to our final feeder, which goes out to our customers. And each zone you'll see overlaps the adjacent zones so that there's no blind spots on the network. But if you detect a fault in your zone of operation, you only want to isolate, pardon me, the zone that is faulted. Obviously, if there's a fault in the generation zone and you turn the generation off, the rest of the network by default will go off because you've lost your source. But if you get a fault, say, on this feeder here, and you have other feeders going off elsewhere, you don't want to lose those supplies. As I mentioned, overlaps, we don't want any blind spots. And we also want to look at their phase discrimination, although in the UK, National Grid generally operates on a three-phase tripping policy. Dependability and reliability are one balancing act you have to do when you're designing your protection scheme, because your protection must operate if there's a fault, because failure to operate is going to do lots of damage. But faults are very rare, so your protection could sit on a part of the power system and not see any faults for decades. But when a fault does occur, it must operate. The use of backup protection and duplication helps with this. Another thing now that most modern power system protection devices do is they have self-testing facilities, so they can internally check that everything is still operating as you would expect while the power system is still energized. But at the same time, if you've got something happening on your network that is abnormal but is not a fault, you don't want your system to trip, because what you don't want to do is to turn a stable power swing, for example, into an unstable power swing by losing part of your generation. So if you've got load switches and faults elsewhere on the network, you need to maintain your supply as much as possible. So for different types of parts of the network, there are different causes of faults. Underground cables, diggers, so people digging up, I've mentioned previously, but also overloading. A cable may have been installed originally to supply, say, a small residential area, and over time more and more homes have been built and the load has gradually increased, and ultimately you actually you unintentionally overload the cable. Leakage into the soil can directly affect the insulation. It can get in and break it down and cause faults within the cable, and also the aging of the cable itself. Over time, it will just deteriorate. So there needs to be some sort of maintenance and plan for that. Overhead lines, as we've mentioned previously, are exposed to the elements. So lightning strikes are common. Anything that's in the air nearby in their electrical or corona area, so kites, trees. If you're near the coast or near a waterfall or something, you may have lots of moisture or salt in the air. Large groups of birds can cause problems if they all decide to roost on the cable simultaneously and all take off simultaneously, causing oscillations which can cause the clearances between conductors to be exceeded, or broken conductors. Say, for example, you get ice buildup, which causes the conductor to come down. Machines most commonly are mechanical damage and unbalanced loads, but as I say, that's not really part of the power system itself, so I won't go into any more detail on machines tonight. So here's a nice busy slide on types of fault. We start on the left. These are all the combinations of fault to earth. So you can have a single phase to earth, a phase to earth, and a three phase to earth. And you could find that a fault starts as a single phase to earth and evolves through to the three phase to earth if your protection hasn't detected. You may also get faults that are just between two phases and doesn't go to earth. And that again may evolve into a three phase fault, but with no earth current flowing. And also, I've mentioned broken conductor. You may have a broken conductor which earths one phase, but the line past the break is de-energized. So these are all typical conditions you may see on UK transmission lines, but they are, as I've mentioned previously, they are quite rare. They don't happen that often. Cross-country faults can happen on very long lines. So the UK generally doesn't have a lot of long lines. It's quite a heavily meshed network. But in a cross-country fault, you could have different faults on different phases on different parts of your network. And also, if you have a parallel line, these are common in some parts of the world, not so much in the UK. You could get cross adjacent faults where one phase on one line connects to another phase on another line. So you would see a face-to-face fault back on the bus. But again, this isn't common in the UK. So if we look at cables, I mentioned about insulation failure. So say you've got a cable that's been running for a number of years and the insulation has started to fail on the A phase, and you start to get a fault developing on that phase. The way these typically appear is you'll get a crack in the insulation, moisture will penetrate the crack, the voltage on the line will then arc across it, causing a spike, but that spike will vaporize the water, driving it out of the fault, and the fault will clear. And then the process will repeat itself sporadically, and gradually, every time it happens, the insulation deteriorates further and further. And eventually, the deterioration gets sufficiently that it becomes a phase-to-phase fault. And at this point, you're now starting to see rapid deterioration of the insulation because the energy levels have grown sufficiently that it can leap across. And before long, if your protection hasn't detected that, you get yourself to a three-phase fault on your cable. And the only way really that the only thing you're going to see after that is a bang as the cable blows up. There are lots of YouTube videos of these things happening. I thought about putting one in, but then I decided they were all too long. But if you want to go and search underground cable explosions, you'll find loads of them on YouTube. Okay, so those are faults we're likely to see. So what type of protection will we be looking at? We have two main classifications, non-unit or unrestricted, and that will operate for a fault regardless of where the fault on the network is. As long as it can detect it, it will operate. So that means if you have a multi-stage protection scheme and your end stage has a fault, the protection on the first stage, if it detects that fault, may operate and isolate more of the network than is necessary. So we need to do some discrimination. And typically that's done by what's called time grading. So you make the protection progressively slower as it gets nearer to the source. Of course, this has its limitations because the equipment on the network will have its maximum loading time that you can withstand the fault. So you need to make sure that your protection is discriminating from downstream events, but also still giving the time protection for your part of the network. If you get to a point where you can't achieve that using time discrimination, you typically would use unit protection. And what this does is it has a specified zone of protection. So you will only operate if the fault is in that zone. So in this case, say you've got a three-stage protection scheme. Each stage will have its own protection zone, overlapped, of course, so there's no bits that are missed by the protection. And then each zone will only operate if there's a fault. So if in zone 1 there's a fault, zone 3 will say, that's not in my zone, so I don't care, I will keep operating. And this is more commonly used in the transmission systems. Non-unit tends to be used more in distribution at lower voltages, but it's also non-unit protection tends to be your backup fail-safe in case your higher level protection has failed. So, types of non-unit protection. The original protection was a fuse. They're still used today in some low voltage systems. On voltage transformers, you will have a fuse as well, and some auxiliary supplies. And they will, as a fuse works, if the current exceeds a certain level, the fuse will burn out and it will break the circuit. Of course, the problem with that is you then have to manually go and replace the fuse to re-energize your system. So overcurrent and earth fault protection devices were developed. 51 is an ANSI designation for a time-delayed overcurrent element. So what you're doing here is you're measuring the current flow, and then you have some sort of activate, some sort of contact and your trip coil, and you will control the energization of your trip coil. There are other non-protection units doing voltage and frequency and rate of change of frequency, but they are not as commonly used. They are used, but not as commonly used because they tend to be very specific to the application. Whereas overcurrent earth fault are pretty much used everywhere. This diagram here shows for a particular level of fault, the different discrimination. I'll come into more detail on that again on another slide. I'll show how that curve is derived. So if we look at unit protection, the two most commonly used methods of unit protection are differential and impedance or distance based. So in differential protection, you have a circuit you're protecting and you have measurements either side of it. And so long as the current flowing in and flowing out of your circuit is roughly the same, allowing for measurement errors, you would say that your circuit is healthy, and anything that happens outside, you're not going to respond to. Feeders, bus bars, transformers, generators, all of them have their own versions of differential that can be applied. You can even do things like vector compensation for transformer shifts and things like that. Today, we very much rely on communications, and we tend to use what's called biased or low impedance schemes because it gives you the most flexibility in terms of how you connect to your current transformers. High impedance and restricted earth fault schemes may still exist in some parts of legacy schemes, but they're not widely used today. These have much tighter constraints on your current transformers, which is why they're generally not used. I've mentioned communications. Pilot wire is a analog. If you think something like 4 to 20 milliamp current loop, it's that sort of thing. You would send a current from one end to the other. But again, that's very rarely used today. Today, it's largely digital communications because that is the norm for most things. So this channel today will be, typically your relay will be plugged into a multiplexer onto a gigabit back hub, and it will be transmitted across your network on a fixed link path to give you deterministic comms delays. I won't go into the details, but that is important for your protection. You need to know how long the communication is going to take. Oops, sorry. Distance and impedance protection works on the principle that if you can work out the impedance on your circuit, you can determine whether the system is healthy or there's a fault in your zone of interest. So this diagram shows what's called a mho, which is an ohm in reverse. And if you remember, I mentioned the UK power system generally is at about 70 degrees lag. So this is your reactive power. So you're about 70 degrees there. So if you've got a fault, it's going to be somewhere on that red line. You would expect it to initiate. It may move after the fault's established, but initially your fault will start somewhere along that line. And the blue line is the impedance circle of your line in healthy conditions. So if you're inside that line, you've got a fault. If you're outside that line, then you're considered to be healthy for your section. It's predominantly used for transmission and sub-transmission, so that's 132 kV and above. They may also use it for distribution feeders, but it's not that common. And it can be used for backup for transformers and generators because you can set your impedance so that it penetrates into the transformer or the generator windings, usually 50%, the midpoint of your transformer. Another method, phase comparison, directional comparison, there are actually variations on the differential scheme, but what you're doing is you're compressing the data you need if you have limited data capabilities. So they're used in parts of the world like Russia, South Africa, but generally not in the UK. There are various other special protection devices, generators, motors, transformers, etc. But they tend to be bespoke to the device that you're protecting. Similarly, you will have auto reclosers and tap changers that are there to control things like auto voltage control for your distribution network. And you have a number of auxiliary devices that are there to interface with the other equipment on the network. So I mentioned earlier, I would come to that curve I showed you for the coordination of our protection. So if you look at this network here, we have a source on the left. I haven't shown any step-up transformers or anything, but assume that source is our distribution network, say, and we have several stages of feeder, and then our final stage is protected by a fuse. So we have 3 fault inception points. For simplicity, I'm assuming that regardless of where the fault happens, it has the same maximum fault level. And what we want to do is we want to make sure that relay 1 only operates for this fault here, relay 2 for this fault, and relay 3, oh sorry, fuse 1 for this fault. So what we do is the fuse has a fixed characteristic, and we will get that from the manufacturer, and it looks something like this. So we will have a maximum fault level and an operating time for the fuse. So as the current increases, the time for the fuse to operate decreases. What we then do is our relays 1 and 2, we will use a protection characteristic that emulates a fuse characteristic. So here, relay 1, so the blue line, relay 2. And what you can do is you can set time delays. So typically you will coordinate your delay at the maximum fault level. So here we've decided what the delays between relay 1 and the fuse and what the, sorry, relay 2 and the fuse and relay 1 and relay 2 are going to be. And we've set the characteristics to reach those points. And then when you plot those respective curves, you see that our set points are here and here. So our setting point 2 is the minimum current at which our relay will start to operate. And setting 1 is our minimum point at which relay 1 will start to operate. And that way we achieve time discrimination. So that if you get a fault here, as I said, your fuse will go first, whereas these other 2 will be time graded to operate only for the faults associated with their part of the network. So that is how you would perform coordination. Obviously, this is a small, simple case, but you may have multiple buses running in parallel, and you may have to grade across sections. So what you may have to do is you may have to divide your network up into zones and grade each zone independently. Differential protection, as I mentioned already, you're looking at your protected circuit. If you have a fault external to your circuit, then the current flowing through, when you do a comparison of the 2, the difference will be approximately 0. There will be some small errors due to measurement errors, etc., perhaps small timing errors, but you expect the current for your differential to be quite low. However, if you had a fault internally, you see now the flow arrows, this is assuming you have a source at either end. If you had no source at one end, you just have a feed in from one end. But either way, when you compare the measured currents from the 2 ends, you will see your current is significantly larger than 0. So that would be an in-zone fault, and you would operate. For example, because both ends are measuring locally and receiving remote ends, both ends will see the fault at the same time, but they will also have intertripping capability So if one end doesn't for some reason see it, it can be tripped by the other end. You may also have intertripping with other devices nearby to switch in local logical schemes to isolate other bits of equipment. Distance protection, what you're doing, we have a source and a source impedance. And at the point that we measure, what we're measuring is the voltage that is generated across our line and our load. Pardon me. And we calculate the impedance at that point by dividing the voltage measured by the current, and that gives us our measured impedance. Now, if under normal conditions, ZR is greater than ZL, which is the impedance of your line, and you would say the system is healthy. However, if your impedance drops below that, so your fault impedance becomes less than your line impedance, then you're inside this circle here. Or alternatively, you may have what's called a quadrilateral characteristic. These are used in parts of Europe, like France, Germany, and associated countries that use similar schemes to them. So we can say that we have two key elements to our distance protection. We have a voltage, which is restrained. So as your voltage increases, the likelihood of you being inside your fault characteristic reduces. So that's said to restrain your protection. However, as your current increases, then your impedance will fall. Therefore, the likelihood of you being inside your characteristic increases, and that's called your operating current. But as I mentioned, with our AC networks, we have complex. We typically have a 70-degree characteristic angle, so we have to do this calculation in the complex plane with active and reactive power. So distance itself will normally operate multiple zones. You will have zone 1. You see here, this section, you will have distance in both directions with an overlap, and they are the high-speed tripping for your in-zone faults. So they should operate for any fault in that zone. Similarly, any fault in this zone will have similar arrangements, and that should operate first. However, if for some reason this relay didn't see the fault, say it's very close to the inlet here, so that end doesn't see it because it's only 20%, and this one, it's such a small measured voltage that you can't accurately detect it, then your zone 2 from the previous zone gives you an overreaching protection. So this is our, if you remember, our overlap of protection that we're talking about at all times. And then just to be absolutely sure, we tend to have a third zone, which is slower again, but much longer reach. And modern relays, you may have more, 6 or more may be available to you, and you can set them up. You can do things like offset zones and all sorts of clever characteristics, but that's entirely down to the requirements of the system you're protecting. So, as I've mentioned, in order to achieve protection, we have standalone devices. So the earliest elements were fuses. They will isolate if you get excessive current, but then you have to have someone go along and replace it to reactivate your system. So to overcome that, the earliest devices used electromechanical forces. So generally you'd have the current would generate electromotive force in some sort of mechanism, and then you have some sort of mechanical resistance, say a spring, which would resist it. And if your current got sufficiently high to overcome that, it would activate contact and operate your protection. And then when the current cleared, that would then release the trip signal again, so the line could be re-energized. Static relays came along around about the 1960s, and they replaced the electromechanical devices with analog electronics. So it's still doing the same comparison, but instead of using a physical movement, it now does a magnitude comparison and then uses that to switch the output decision. Digital relays came along in the 1980s. And again, that's an evolution of technology. So in the 1980s, you would have had the widespread use of the early 4-bit, 8-bit and 16-bit microprocessors, but the functionality was still very limited. You generally didn't have user displays or anything like that. It was all done by some sort of plug, switch and a process to configure. And generally there were still single function devices. Today, the diagrams here show we're in the era of numerical relays. So you have multifunction devices. They use embedded processing capabilities. They usually have some sort of display capability as well, and communications, so that you can perform multiple protection functions in a single device. Okay. So I'm just checking my time. How far am I in? It's gone quite a while. Anyway, DC protection. So that's as much as I'm going to discuss on AC protection, because I'm just focusing on the principles tonight. I'm not going into detailed applications. So now if we look at DC protection, this is a nice valve stack in a DC valve hole. So that's where the voltages and currents are generated for your HVDC systems. I'm not going to go into great details of how these operate, because there was a previous presentation by Turklin on this, and if you want to see that, that's on the IET website. You can go and view that. The key points to consider are, what are the HVDC topologies likely to be? The most common today is your bulk power point-to-point, where you have an AC network at either end, and you're converting from AC to DC, transmitting your power, and then converting it from DC back to AC. So there have been links like this in operation for many decades now, over 50 years. It's the most common method of HVDC system. We also have what are called back-to-back systems to couple AC systems, but effectively all that is, it's a point-to-point with a very short connection between them. So in terms of what you do for protection, it's very similar. Multi-terminal DC systems, there are some trial systems in China, but none that are widely deployed anywhere at the moment, because of the challenges at this node point. You need very fast breaker technology to be able to protect your system should you have a fault on your DC network. And it must be done with VSC, because the LCC approach just is not practical for this configuration. But as I say, as today, it's still really something for the future. It's not widely applied across the world's power systems. So an HVD system, if we look primarily at a point-to-point system, it normally has 3 stable states. It can be the shutdown, so there's no energy in the system at all. It can be in what's called a block system, where your converter stations are energized, but there's no flow between them. And then it can be in the operate state, where there's energy flowing from one side to the other. You may have other transient states within the system, standby charging, etc. But these are all transient, as the name suggests, where you're transitioning from one stable state to another. There are 2 main flavors of HVDC in operation. Line commutated converters, LCC. They use the AC network to do the commutation, which means that it's the switching forms a loop through the AC in order to achieve your waveform. It can be achieved using diodes, but that's not really practical for large high voltage systems. Typically they're done with thyristors, which have the advantage over diodes in that you can control when they're turned on, which allows you to control voltage levels. Although you can't turn a thyristor off once it's energized, you have to wait for the AC side to go to 0 to de-energize the thyristor. So that has been in, those are the, well, today they're using thyristors, but the original LCC systems use things like mercury arc valves and things like that. They've been around for many years. The more modern, or sorry, the more recent developments in high voltage DC are based around what's called voltage source converters. So these use devices called insulated gate bipolar transistors, IGBT. It's basically like a very high power transistor that you can switch on and off. There have been various evolutions over the years, starting with pulse width modulated versions in the early days. Today, the most common use is what's called modular multi-level converters, where you will build a module of a fixed voltage level, and then you stack them to build to the voltage level required. A typical module will be, say, 2000 volts, 2 kV, and capable of supplying maybe a few kiloamps when in operation. So when you stack them up, you can get significant amounts of voltage and current generated by these devices. Another advantage VSCs have is that the way LCC systems work, they generate lots of harmonics. So you have to have filters to reduce the harmonics on your AC network. So on a LCC station, you will see a large filter bank around the converter station in order to maintain the noise profile required for the AC network. Whereas with VSCs, it's much less of an issue because you have a much finer resolution in your voltage waveform generation. Okay, so if we look at protection on HVDC, we have two real zones of interest. We have protection within the converter and protection on the line. In the converter, we have the transformer protection, which is effectively AC protection on the transformers from the AC to the DC side. And we have valve protection, which is protection of the power electronics, including the thermal model. On the line, we're just purely protecting the line itself, DC, and we have two protection operations we can take. We can either block or we can shut down. Typically, if the fault's on the line, you can block the line but keep your converters energized. But if the fault's on your AC side, you generally have to shut down because you don't want to propagate faults onto the AC network. Overcurrent, as I mentioned, your valve and transformer currents are measured. If you have an overcurrent on the local end, you will shut down locally and you'll send a signal to the remote end to block so it doesn't drive energy in from the other end. Similarly, if you have over or under voltage on your valve and transformer, you will locally shut down and you will send a block to the remote end to isolate this part of the network. If the fault is a transient thing in the local network, you may be able to close it, but typically if it's a fault in the transformer, you will probably have to do some investigations before you re-energize. Also on the transformer, there will be a form of differential. So typically you will have a star on the AC side and a star delta arrangement on the DC side to give you a phase shift between the two legs of your converter station. And your differential, it works the same principle as on AC. The sum of the currents on the low voltage on the DC side should be the same as the currents on the high voltage AC side. And again, if you have a fault, you block the remote end and you isolate and shut down the local end. A special case for DC protection is if you're running a IGBT for a VSC system. I mentioned you can turn them on and off, but IGBTs have a maximum switch off current. So say, for example, this IGBT has a maximum switch off current of 3000 amps and we're transmitting 1000 amps, and then a fault occurs and we suddenly see a rapidly rising current profile. If we switch off at this point here, after 129 milliseconds, we're less than 3000 amps, so we can switch off the IGBT and we can block the valve at that point. If we just wait another 9 milliseconds, we've exceeded the 3000 volts and we no longer can isolate and block with the IGBT, and then we're into the realm of having to shut down the AC side. So this is a bespoke function for VSC systems. Thermal models are also used because as the current flows through each valve, it produces heat, and what you don't want is for the switching device to overheat and burn out. So each device will have its own thermal model running, and it will block if you're approaching thermal limit to prevent you from using it. And this prevents the spread of thermal cascades across your valve. The details of this are usually bespoke to the manufacturer, but there are some standards on people like Seagray and IEEE published thermal modeling standards that you can look at. If we now look at line protection, the two base protections for a HVDC line are overcurrent and overvoltage. Because what happens on the line is totally controlled by the power electronics, if we detect a current or voltage fault, we can just block locally and send a signal to tell the remote end to block, and we can remove the current flowing in the line, but we don't have to shut down the converter stations themselves. Similarly with AC systems, because we have communications between the two ends, we can actually share the measurements at either end, and we can perform a differential. So if you have, say, 1000 amps being fed in at this end, and you're only seeing a few tens of amps coming out the other end, that suggests you've got a fault in your cable, and you can again perform a differential block locally, and you can send a remote block to the other end. Of course, anywhere you detect a fault in the cable, the likelihood is it's going to be a permanent fault, and some investigations will be required before you can re-energize the system. Okay, so there are some other, again, bespoke protection methods used in DC protection, but those are the primary functions that are used universally to protect the scheme, because it's all embedded within the converter station. So if we look now at what's the sort of the active development in protection these days, one is a traveling wave detection, and this is an interesting one in that it has applications on AC systems and on DC systems, because it gives you high speed detection of faults, and also allows you to locate them, which is going to be important when you're performing multi-terminal DC networks. Network stability, wide area protection have been a key issue on power systems for many years, primarily because generally what's happening is the demands on the system are growing, pushing you ever closer to your network stability limits. Therefore, you need to continually improve the technology to allow you to maintain that stable response. And I'm going to touch on a thing called demand side response, which is where you actually have customer load that accepts the disconnection in return for some sort of incentive. So if we look at traveling wave detection, here we have a line from L to R, and we have a fault at some point on this line. At the inception of the fault, you will get a wave propagating, as shown by here. You'll get a pulse, typically a very high frequency pulse generated at the very moment the fault occurs. and this will propagate across the line at close to the speed of light because of the high frequency. And if you're measuring at both ends, and you can measure accurately the time it arrives at either end, you can use an equation like this one here to use the difference between the two time measurements to calculate where in percentage terms you are on the network. It is possible to also do single-ended calculations by using reflected signals, because at every point on the network where there's a change in impedance, you will have a splitting of the signal. Some will continue to propagate on and some will be reflected, and then again it reflects back. So if you can measure those 2 points, you can actually calculate the round trip delay and calculate whereabouts on the line you are. Obviously, this theoretically continues on infinitely, but every time you attenuate the signal till at some point you won't be able to measure it. So say on AC networks, this is useful for very long lines. If you've got a fault and you need to have someone go out and inspect the line, this can give you very accurate position information so that someone knows where to go to look at the line. On DC networks, it may also be very useful because faults tend to propagate at the same speed as the traveling wave. You may want to actually have some sort of high-speed detector which will instantly lock your line on this detection, because the even things like the 3 millisecond delay on your protection may not be quick enough. You may be able to get faster using this, but this is something that has not been widely deployed on DC systems up to now. Network stability sits in this sort of middle ground. You've got your traditional protection schemes, which are very localized and operate in the millisecond arena. And you've got your energy management systems, which are largely centralized, but operate in the terms of minutes. And you now have this middle ground wide area system integrity, which are faster than your energy management systems, but not as fast as your local protection. And what they're doing is they're monitoring your network and trying to maintain stable power flows. But all of the constraints of your local protection, dependability, reliability, security, and selectivity still exist for this middle ground. PMUs, phasor measurement units, have been widely deployed in some parts of the world. National Grid has deployed some for trials, but it's not across the most of the network at the moment. And they are widely being now used in these system stability systems to then feed into your energy management systems, and they can give you visualization of hotspots on your network in close to real time. I mean, typically a phasor measurement unit will be giving you 50 measurements per power system, 50 measurements per cycle. Sorry, no, 50 measurements per second. Sorry. So even so, that's a lot faster than the several minutes you would have on your SCADA systems. Demand side response. Electricity Northwest did a study on this. What you have on your system, you have your permanent load and your DSR load, which is your delta. And under normal conditions, you have two feeders supplying them. You get a fault on one of your feeders, but your load is less than the protection setting for this feeder, so your system stays healthy, but your demand side load is switched off because you want to maintain your margin. Now, in that scenario, you get the fault. You go from a healthy system to a fault on the one feeder. This time, your load exceeds the setting for this line. So now this line trips as well, and you've lost all your load. What you do then is you reconnect your permanent load, but your DSR does not come back on. And that gives you a quicker response to restore your load. because you've shed some of the load that was there prior to the second line tripping. You can also use an inter-tripping scheme so that if you detect a fault on the first feeder, you trip the second feeder as well. You shed the DSR load at that point. Then when you reconnect, you go back to a healthy state. So this is still in trial proposal stage at the minute. But as we move more and more towards renewable sources of energy, it may be that we need to move towards systems where you have incentives to people to say, okay, if you allow us to switch you off in these contingency systems, then we will reward you in some way. Okay, so what are the future challenges for UK power system protection? Renewables is a big one. More and more we're becoming dependent on solar and particularly wind power. There have been many days in the past couple of years where the wind generation has matched the demand for the UK. And also we're getting more and more power electronics replacing the old conventional rotating machines, which means that the system is less stable than it was. We're also going to see large scale storage coming online, and we're all aware of things like Tesla power walls and stuff. And there are trials in, I think it was in Nice, there was a large urban battery system trial done. But things like electric vehicle batteries being used as distributed storage are also things that are being investigated. Loss of inertia and artificial inertia are areas of interest. Loss of inertia is where you're replacing your large rotating machines, which give you that mechanical inertia to the system, with power electronics, which has no inertia. But there's experiments going on with National Grid in the south using wind farms to generate what's called artificial inertia to inject into the transmission system to give stability to the network there. So they're using power electronics to generate reactive power instead of active power. Islanding and loss of mains will be a major issue if we become dependent on these things, because the way the power grid code is at the moment, you have very tight voltage and frequency limits in which wind farms and solar farms can stay connected to the grid. And if you're disconnecting, what you don't want is to have small islands that are being maintained by your local generation, but running independent to the main grid, because the danger is A, you may find it difficult to resynchronize and reconnect to the main grid when you need to, and B, there may be situations where it's actually unsafe because you've got voltage and current flowing where people think the system is dead, and you could end up with unwanted interactions with live circuits. System stability, as I mentioned, is a long-term issue because they're forever trying to get more out of existing assets, because the planning restrictions on new overhead lines and things like that, and cables are so restrictive. They're always looking to minimize the margins of the system they're running today. And then multi-terminal DC systems, breakers is still not mature. There's lots of fanfare out there, but they still haven't really got to that maturity level that's required for this to become feasible. And fault discrimination on the grids as well, because if you've got a fault on a DC grid as opposed to a point-to-point, you don't want to switch the whole network out. You want to be able to isolate just portions of it. Okay, I know I'm slightly over the hour, so I shall get into my conclusions here. AC and DC networks, they have common principles of protection, but they have different application domains. So overcurrent, earth fault, overcurrent, overvoltage, differential are protection schemes that apply in both domains. But on AC protection, you have a dedicated device, whereas on DC protection, it's integrated into the converter station. And how you respond to the fault on an AC system is different to how you respond on a DC system. AC networks have inertia and they have reactive power, and that gives them time to actually validate what's going on before they take actions. DC networks don't have that luxury, so they just have to react instantly to what's going on. Increasingly, renewables and power electronics are becoming ubiquitous. In the future, it will become the norm for storage systems to be connected to the network as well, so that your renewable systems can charge storage, whether it be batteries or hydrogen or thermal salt or all sorts of different schemes exist to store the energy. And then that will be used power electronics to generate the signal when it's required, the power is required. So therefore, system inertia and the stability that it provides will become critical. Okay, I shall hand over control at that point back to, I think it's to Bernard.
Yes, thank you so much, Brian, for providing such an insightful information about this complex subject. Before we move on to the question and answer session, I will just give a breather to Brian to just have a short break before Emilia starts to raise the questions that were raised on the Q&A panel. Yeah, it's an interesting topic. We see that the power system is changing these days due to the target to reduce the emissions, CO2 emissions in the industry. So from basically from traditional generation power systems, that's now changing with a lot of the embedded generation. So this will change all the short circuit levels, and I believe it will bring some challenges to the future networks as well. I've seen some questions regarding the CPD certificates and slides. So there are links provided for the CPD certificates. You can access and download them they were provided in the chat box. So they are not individual specific. So you have to download and type your name on them. And for the slides, they won't be provided. This recording will be uploaded to our YouTube channel. Again, the link is provided in the chat box, or you can just simply go into YouTube and type IT Northwest Midlands. So you will be able to access our channel and see all the events that we had so far uploaded in it. And you can rewatch it again, or just recommend it to a friend who is interested in this topic. We touched as well on HVDC protection. So we had 2 past webinars on HVDC topic. So if you're interested, again, going into our YouTube channel and watch them, so you can learn more on that topic as well. We'll have future events coming, so please go into our IT Northwest Midlands website to check out what our community is doing here, and you can see our schedule for upcoming events as well. And yeah, that's pretty much. If there's anyone from this area would like to join our community in the IT Northwest Midlands, please don't hesitate to contact us. So if you would like to volunteer as well into the upcoming events, please do not hesitate to do so. And now I believe we can move to the Q&A session. I've seen that there are so many questions, interesting ones. And over to you, Emilia, if you're ready to read out the questions.
Thank you, Bernard. Thank you, Brian. I've got Mehu today. Mehu is going to assist me in asking Brian questions that have been raised by the attendees. Because of the way you've delivered the talk, Brian, you'll find that most of the questions that we'll ask you first have got to do with AC protection. And then the other last of the questions are based on DC protection. Okay, so I'll make a start. One of the questions that was asked was, how are DNO's geographical boundaries determined? Any thoughts on that?
It comes down to government policy. They decided how to divide the country up. And then what's happened, for example, Western Power Distribution, the Midlands and Wales and the Southwest used to be separate distribution networks, but when they were privatized, Western Power Distribution basically took over these other regions. So you could divide some of those networks into smaller pieces, but they're operated as single systems these days.
Thank you, Brian. Just to say to the attendees as well, all the questions will be uploaded on our Northwest Midlands IET website together with the answers. Obviously, give us a few weeks or so after the event to get all the questions answered, and then we'll upload the questions and the answers as well. So if we don't ask your question, or even if you want the answer, that will be provided to you later.
Okay, and similarly with transmission system networks, it's a legacy back to the 1930s when the government then decided how to set them up. So they've been that way for a long time.
Thank you. Mehul, do you have a question?
Yeah, Brian, another question is that on the one of the attendees has asked that why does most of the west coast have no wind farms, whereas that they are all most of them distributed all along the east coast?
The simple answer is money. In order to make money from your wind farm, the closer you are to London, the more money you will make. So the funding tends to go more towards ones in the southeast because they're supplying London, which is where the money comes from.
Makes sense, yeah. Yeah, and go on, Emilia. Yeah, you can go. Yeah.
There's an interesting question from Christian. Are there any plans to increase grid voltages even further than 400 kV, like they have in some other countries? And does this bring any advantages to the UK or not really required?
I don't think the UK network is big enough to really justify going beyond 400 kV. The networks like Hydro-Quebec, which are at 735 kV, Eskom South Africa, the Brazilian networks, which have higher voltages, they tend to have lines which are thousands of kilometers long. UK, the longest lines are only a few hundred kilometers, so it's not really economically viable.
Yeah, one of the question Brian is that on backup or basically duplicate protection, do we apply the discrimination or it's just a time delay?
Backup protection will generally just be a time delay, because your backup, as it suggests, is it's there in case your main protection has failed to operate. So if you get to that point, say your main protection fails to operate and your backup protection has a delay of 150 milliseconds, it will then just say at that point, oh, main protection's failed, I best operate. It's purely for that.
Yeah. Emilia?
Yeah, so I'm also interested in climate change, and I'm hoping to have my next event on climate change. And this question touches a bit of climate change as well. With weather patterns becoming more extreme, lightning or surge protection seen as an increased risk where more investment is required.
Yeah, absolutely. Lightning is a phenomenon that happens all over the world. And the UK generally doesn't get a huge amount compared to some places, but it is still something that can cause over voltages on the network, can cause conductors to arc and give phase to phase or phase to ground faults, etc. So you need to protect for that. And also not just lightning, but high winds also are a danger to the conductors because you get them oscillating in the wind and potentially the clearances get compromised and you get some faults. So as the weather changes, then the effects on the protection on the power lines is going to change as well. Most UK power lines are rated on a standard temperature and humidity profile. If that profile changes, it may change the way the system operates.
Thank you.
Yeah. So another question is from Andy. Basically, what he's trying to ask that relay capabilities now are available due to the technology advance in making relays more capable.
Mm-hmm.
But the pool of the engineers who can work them is getting smaller.
Yes.
Any thought on that?
Absolutely. It's not a new thing. This has been going on for decades. There's a serious shortage of engineers in power systems, in AC and DC systems, in communications, backups, teleprotection. The whole arena is actually, if you're an engineer, it's a good thing in terms of there's lots of opportunities out there for you, but for the industry as a whole, it's a real issue. Particularly in the UK, because for some reason people in the UK don't want to become engineers. I don't know why. Yeah. Whereas if you go to Asian countries, especially, engineers, or even parts of Europe, engineers are seen as it's not a respected profession, but in the UK, we don't seem to get that respect at the moment.
Thank you, Brian. I must say that photo behind you, that's a good one for relays, right?
Yeah, it's a substation. The relays you can see behind me are distance relays made by Alstom back in the day. And this is a substation I worked on a few years ago.
Good.
And I think Lotto is also implemented. I can see the locks on the panels.
Oh yeah, absolutely. Has to be safe.
Yep.
Yeah.
Okay, this question, how precisely can traveling wave detection locate a fault?
There's been lots of academic work on this, where they can say they can locate it down to within 1 meter on a 100-kilometer line. The only trouble with that is that the equipment required to do it would be so expensive, it would be cheaper just to replace the line. Because to get very accurate fault location, you would need extremely high frequency measurements, and that is generally expensive to do. So there's, like everything, it's a cost benefit assessment you need to do.
Mm-hmm.
But Schweitzer Electric are promoting traveling wave a lot, so they've got a lot of material if you want to go and read up on it.
Okay, thank you. Okay, are you okay to continue for a little bit more, Brian,
Yes,
with
I'm
the
fine.
questions? Okay.
I'm okay.
Okay. Mehul?
Yeah, so this one is also interesting, Brian. What basically he wants to ask that have the changes of the generations at the present the more and more the renewable, basically solar and wind, they are connecting to the generation, right?
Yeah.
So I mean the demand of this renewable the generation, how it's affecting the protection. Is it basically affecting?
It will do. If we had a power system that was purely fed by power electronics, the profile of faults would change. because the power electronics doesn't behave in the same way as a conventional generator.
Right.
So you wouldn't get these large current spikes with voltage drops because the power electronics would limit itself in what it actually put onto the system.
Right.
So
Okay,
it actually makes the job for the protection a bit more difficult on the AC side if you had purely the power electronics feeding it.
Right.
Okay, just to say, a lot of people are also still asking whether the presentation will be online later. Yes, it will be. We will upload the recording on our IT website, not West Midlands website, a few days after the event. So you'll be still able to watch the event, see the slides, and also the Q&A session and everything else that took place. There is a question from Alfred. What is the fault contribution of full PV converter at the point of connection?
It will be the maximum output of the converter capability. As long as it stays within that voltage and frequency profile, as soon as that's exceeded, the converter station will then disconnect.
Thank you.
Yeah, another question is the National Grid are looking to connect the synchronous condenser onto the HV network. Do you have any view if this will provide the required inertia to maintain system stability?
The issue is going to be scale, isn't it?
Yeah.
But you're going to have, in order to maintain the inertia required, you're going to have huge amounts of those connected to the network if you took off all of your existing thermal. And so, like everything, it's feasible if you do enough of it, but is the cost? I don't know enough about the cost of synchronous condensers and their functionality to be able to say for definite. But it's one of these things. If you put enough of it on, it will work, but it's going to be. But then you have to manage that as well. And then what's the life scale? How long will condensers last? How often do you need to service them, take them out of service, etc.? It's a whole topic in itself, I guess.
Right.
Perhaps you can get someone who knows about this to do a talk. I'd be interested to know.
There is a question on generation. So have the changes of generation, which is more solar and wind and demand, affected the protection?
Sorry, repeat that again.
Have the changes of generation, which is more solar and more wind, and demand, in brackets electronics, affected the protection?
It's starting to. It hasn't up to now, because what's tended to happen is the regulators have specified how the renewables connect in, and they've always assumed there will be a base load from traditional sources there to keep the system running. But as you know, coal generation is pretty much all offline now. Most of the current UK nuclear power stations are going offline over the next decade. Hinkley Point C is due to come online in 2025, but that's looking like it's slipping back towards the end of the decade. So more and more we're going to be dependent on wind power, especially to keep things going. And the danger is particularly things like distance protection. If you start injecting volts and current in the middle of a line with a new interconnect, it changes the impedance that your protection relay sees. So you may start to see distance protection being compromised, for example.
Thank you.
So, Emilia, do we need to go further more, or because now time is running out? Yeah.
Exactly. Thank you very much, Brian. We'll hand over to our one of our colleagues, Bena, to do a vote of thanks. Thank you, Mehu. Thank you, Brian.
Thank you, Emilia. Thank you, Brian.
Okay, thank you very much.
Thank you, everyone. thank you for those who attended this webinar. You've been great. I've seen that most of you stayed until the end. And thank you for the great questions. Thank you, Brian, for providing this webinar to us and to the audience. Thank you, Alison, for opening the webinar and introducing Emilia, who is the host of this event. Thank you, Emilia. We will continue to expect more events like this from you. And thank you, Michael, as well, for helping with some of the questions from the audience. And thank you again if you would like to obtain your CPD certificate, just go to the IT Northwest Midlands website. And if you would like to watch again the webinar, just go to our YouTube channel just by typing IT Northwest Midlands. Thank you so much and have a nice evening. Until next time.